Welcome everyone. In this video I'm going to show you another temperature sensor dash data logger. So this guy that you can see here is a DS18B20 based thermometer, and these are the thermometer units. So the chips are encapsulated in these small stainless steel units, and I put some heat shrink tubes there just to distinguish them. So RGB, like the colors on the scale, and black, so I know that channel 1, channel 2, channel 3 and channel 4. And yeah, basically this is the unit. So just a few sentences about this very clever and nice chip. So this uses a so-called one-wire interface, which basically means that you just need one wire to use this device. So I mean, other than the ground and power supply, then you just have another one like output line or something like that, and then you can connect up several parallel devices to the same Arduino pin, and all you need is just a simple 4.7K resistor as a pull-up resistor, and that's all. So what I did here, I hooked up 4 with my device, because previously I was using this LM335 thermometer with roughly the same setup. So there was a display, there was a switch, or there were 2 switches, and there was an SD card slot. So I used it as a data logger, but there I was not able to make them entirely waterproof. And then these chips are waterproof, and it's very easy to use them in those kind of environments where I want to use these chips. So for example, I want to measure the water temperature in my water cooling system, or in the bath that I'm using for the cooling and freezing test for the Peltier units. And yeah, so I got some leakage, some water got into the casing that I made. So luckily I ordered these things last week, and they have arrived yesterday, so I could assemble this device. And what this can do is it can measure the temperature between -55 and +125 degrees Celsius. So it's pretty much okay for like human temperatures. So you can check the temperature of your coffee, or you can check the temperature in your freezer. So that's like that covers the range of this almost entirely. And it's very good because it's rather precise. You can change the resolution of it. I don't exactly remember, but I think it's from 9 to 12 bits. And each devices have a unique 40-bit, 64-bit code, which means that either you just plug in everything and let the library take care of these units, or you can check them one by one, what is their code, and then you can refer to them in your Arduino code by their codes, which is their ID basically, and you can handle them like that. But I will just use the regular searching for the different devices, and I know that I know which device is the first, the second, and the third, and so on. So that's not an issue for me. So about this small box, I did not record the assembly phase because I think it's boring. But what I want to tell you is that you should not use small boxes. So I learned it the hard way, but the wires are quite rigid and they take up a lot of space at the end. So it's just a bit painful process to put everything nicely in the box. But now it's everything here. And I mean, I can really show you that this is not a too big box. So this is like 6.7 centimeters in this direction, and 6 centimeters in this. And the depth of the box is, let's say, almost 3 centimeters. So it's a small box, but it has this OLED display. So 128 times 32, and it can display 4 lines. And then we have the toggle switch. In this case, it's a bit counterintuitive, but for me it's not. This is the off state. So in this case, we are not logging on the SD card. And when I do this, there will be a logging start. So that means that we started to write on the SD card. And yeah, the 4 outputs, so I just made a notch here and it's tightly holding these heat shrink tubes, so it's quite nice. And then front panel, so we have this, I think, USB-B connection, and then there is an SD card now inside. These are not the nicest cuts, but whatever. And then these 2 screws are holding together the case. So yeah, this is all. I turn it on and show you something. So I connected it to a USB charger. And yes, I'm very sorry, but the numbers are very small. And maybe the display is a bit flickering because it's updating. But what you see is that we have a channel 1, channel 2, channel 3, channel 4, and the elapsed time in seconds. And then there is a 0 here, and that is basically the status of the switch. So when it is 0, then we are not writing on the SD card. And when I will flip this down, then this should be a W here. So I hope you can see it, but check it at the tip of my finger. That should be a W. Yes. So now it means that it is writing, and you could see that the timer restarted. I think this is a somewhat smart idea. I will explain it when I explain you the code, but whenever I flip the switch down, I will reset the timer, because I always assume that when I start the measurement, I want to start from the 0 time, and I don't want to just continue from the time which is on the elapsed time. So then now I flip it back. The W should go back to 0, but the time will of course continue, because we don't care about that when we are not logging on the SD card. So this is 0 now, but this hasn't changed. And now just to repeat it, I flip it down, and this should be W, and this should be 0. So now 0, 1, 2, and then W. And yeah, I just hold this, so this should be channel number 1. And it's going up 29.5, 30, 30.1, 30.2, 31. Yeah, so it works. So you see, it's a small, nice device. And now I will be able to measure everything in a better way, because these are safer to use. So yeah, now, and before starting with the drawing, I will show you the drawing of this circuit, of course, and the source code. I want to show you something as a sort of flexing or something. So I have more of this, and these are much better in that sense that they have these 3-pin connectors, so I can hook it up into the sockets. But why I'm showing this to you is to keep you somewhat excited that I already started to work on something else, which is basically a test unit for a Peltier cooler, or any kind of Peltier cooler. I will use 4 different thermometers. So one will measure something related to the hot side, this will measure something related to the cold side of the Peltier cooler. Something will be measured by this, for example, the temperature of the cooling water, and this will be measuring something such as the ambient temperature or the outlet temperature of the fan, or something like that. But I will also measure the current running through the Peltier device and the voltage on the Peltier device, and I will also calculate the power consumption and things like that based on the measured values. So that will be like a tester unit for the Peltier. So stay tuned, and also I want to ask you to subscribe if you want to get updated regarding these or other cool projects, because now I started to receive the parts that I ordered recently, so I can show you many cool projects, mostly measurements and things like that. So I think I talked enough about this, so there's nothing else to tell you. So I think I just remove this from the power source, and then I bring this to the computer, And first I just show you the wiring, and after that I show you the source code and I explain everything, mainly maybe line by line, and I will also demonstrate how the data looks like when it comes to the serial port, and so on and so on. So let's go to the drawing. So this is our drawing, and I hope I haven't made any mistakes here, but if I did, let me know please. So let's start from the Arduino. So you can see that we have several devices hooked up to it. I think the most simple would be the OLED display. So let's just go up. So that device uses the I2C as a communication standard. So it will use the A4 and A5 pins of the Arduino. And the A4 goes to the SDA, the data line, and the A5 goes to the clock SCL. And of course it will need some power and the ground connection, so they make quite much sense that the VCC goes to the +5 volt. So I made this rail and also in the bottom rail to 5 volts. And then of course we have the ground connection that is also connected to the ground. And then we go left, so this is the toggle switch. So one pin goes to high, and then we have the other resistor which goes to the ground, and then this junction is also connected to the other part of the toggle switch and goes to the D10, which is our pin that we will read at each loop, and we will see if this switch is changed or not and what is the status of the switch, whether it is high or low. So that's all. One comment about this resistor, as it is written here, it is 10 kilo ohms. Let's go to the 4 sensors. So I have 4 sensors, as you could see it on the previous demonstration part. So nothing else is done here, just having them hooked up in parallel. So the green line, basically that's the data line or the communication line, and that goes to the D5 pin, as you will see it in the source code, but you can adjust it to anything else basically. This one is the ground everywhere, and this leg is the +5 volt. Don't run it higher than 5 volt because it's not compatible with higher voltages. And you'll see that at the end of the rail or bus there is a pull-up resistor which is 4.7 kilo ohms. And then the last device that we have is the SD card unit. And as you can see from the names of the pins, this uses the SPI device or SPI communication. So we have master out, slave in, clock, master in, slave out, and the chip select pin. So this is using 4 pins instead of the 2 pins which are used in the I2C for the OLED. But it's fairly simple. So the chip select will go to the D4. We will define this in the source code. And then the MOSI goes to D11. SCK goes to D13. And MISO goes to D12. And I will put these numbers also in the source code, I think. And basically that's all. But since it's written here as well, I think it's not really necessary to put it in the source code. So this is the drawing. I think it's fairly simple. I think you can easily recreate this kind of connection, and it should work because I basically first drew this and then connected everything on my board, and you could see that the board was working. So now let's jump to the source code. So let's check out the source code, but before that let's check out something with the library manager. So you go up to the sketch and you go to include libraries, and after that you go to manage libraries. So once this window pops up, you have to wait usually a little bit, and then you type in Dallas temperature and search for it. So you can see that for me it's already installed, of course. So you have to include this library or download this library to your library collection. This will be one of the libraries which are used by this DS18B20 chip. And then we have another, which is the one wire library, and that is the Max 31850 wire, and you see that it's also installed for me. So just please install these two libraries and everything will work with your chip, with the thermometer chip. So we have this, and then I included the libraries and everything works well. This is a generic SD card library, and then this is another very important library, because instead of using the graphical library, which is basically the default library for these kind of OLED displays that I'm using, we are using the ASCII library, which is much less demanding, let's say. So it will not use the dynamic memory and the storage space of your microcontroller. And this is crucial in the case of the Arduino Nano, because if you use the regular or default library for this kind of OLED display, you cannot use anything else with the Arduino, or you cannot create a lot of variables and stuff like that, because that library just takes up all the space. So avoid that and use this. And then here we say that we want to attach this one wire bus to the pin number 5. So the bus is basically that collection of parallel connected DS18B20 chips. So that's what we have. And then we just do these setups. And then we have a device count. That is basically just the Arduino goes, or the library goes through the connected chips and counts them. So if you have 5, then you will have 5 in the setup and so on. I think I forgot this inside. I was testing something. I was trying to calculate the average value of several measurements, but these chips and also printing on the OLED display is very slow. So then that failed. So please neglect this line. We can just get rid of it. And these are basically the 4 thermometers. So T1, T2, T3, T4. And then we have this file on-off button, which is this toggle switch. And I put it on the pin number 10. And we have the writing enables variable. So when we switch the switch, we will change the status of this. And we are not using the attach interrupt. We just put a digital read in the loop, in the main loop basically. And at each loop we check the status of the switch. Since we do not need high speeds or things like that, it's enough to check the speed, check the status of the switch at every iteration or every loop. And then this is the status. This is for my funky trick. I will show you why I do this, or why I need the status of the switch. And then we have this start and elapsed time. This is just to measure the time for the acquisition. And then we just create the display object. Chip select pin for the microSD adapter, and then another object for the file creation, which is the file on the SD card. And then we go into the setup. So we start up the sensors, which is for the thermometer chips. Of course, we need the serial. And then we go to the resolution. We can set up some different bit of resolution. Here we use 10 bits of resolution, which means that the temperature's resolution will be 25 degrees Celsius. This was a typo here, sorry. And then this is what I mentioned previously. So the library just counts the devices. So I will show you when I open the terminal. And then we have this file on-off button or switch. It doesn't matter if you have a button, that's also perfectly fine here. But then for button, you may be, if it's not an on-off button, but it's like a push button, then you need the attach interrupt, but here I just use the toggle switch, which is an on-on switch, so I just have to define that we will use it as an input. And then these are just some regular stuff for the display. You can copy paste these things. You can change the font, check the header files. I don't know which one, I guess this contains it, but you can check what kind of fonts you can use. And also you can change the font size. I used the font number 1. I tried the font number 2 or 2 times, but that was too big. So I could not fit everything on the screen. So maybe it would be nice to have 1.5, because that would be just perfect for my requirements. And then we just clear the display, so we are ready to write on a clear display. Another pin, which is the chip select pin, we have to define it as an output, of course, because we will write on it something. And then we just try to initialize the SD card. And we say that if there was no SD card in the slot, then yeah, we just print some message. And previously, I was using this part of the code for my LM335 logger, data logger, but I just get rid of this, so we don't need. But basically what this does, maybe you will need it, so I keep it in the code, that if it finds a file with a certain file name, in my case this is the temp.txt, then it will delete it and start a new file. But I don't want that, because I want to continue writing into the same file, so yeah. Then we start our timer. So our start time is the current time, or the current elapsed time in milliseconds. So the milliseconds starts the counting when you start up your Arduino, when you plug it in, basically. And then loop, it's quite clear as usual, or I usually try to keep it clear or clean. So first we have to read the switch status. So I want to start the loop with that, of course, and then we read the sensors. That's the second most important part. And after that we have to print the data from the sensors, and we have 3 different places. Of course, we print it to the serial port, and then we print it on the OLED display, and finally we write it on the SD card. And I have 300 milliseconds of delay, and this is basically like 2 Hertz or 1 Hertz, so every second or every 0.5 second, because these things take time. So I haven't measured it, but they take some time, so then it doesn't really important to have this as a very large value, like 1-2 seconds. But of course, if you need something like you just want to measure every 1 minute, then you change this to 1 minute. So let's go through the functions. So in the read sensors, which is basically the second thing, we start the timing, or we measure the time again, and then from that we get the elapsed time. And we ask the library to get the sensor temperatures, and we get each indices, and we know that we have 4 sensors. So I manually coded these things. I believe that you could do this with some for loop or something like this, or a while, but I just wanted to keep it like this. So I knew that I have 4 sensors, and then I just manually do all the 4 sensors. This is a bit more complicated, so we print something on the OLED display. That happens here basically, but yeah, I just have this order of functions. So we are using this 128 × 32 OLED display. And first of all, we clear the display again, despite the fact that we cleared it in the setup. We always have to clear it in every loop, because first we have to get rid of the previous data and then write the new data. So we put the cursor in the origin, and here I have to notice that in this case you use these things, these numbers, as pixels and not as blocks. If you use this 16:2 LCD, which I used in the LM335 project, then you move the cursor by blocks, but here you move it by pixels. So if you mess up these numbers where you move your cursor, then it can happen that you make the numbers overlap, so you wedge your data in between another data which is already there. So be careful with this, but you can like trial and error see how they end up on your screen. And then I just print some numbers, so I know that this will be the channel 1, and I print the value from the variable which was determined or obtained here, and I just want one decimal, so for example 27.7 or something like this. And then here I make 2 spaces, and then second channel, and then I finally make a line break after this is being printed. Here, if the writing is enabled, which means that we are writing on the SD card, then in the very end of the screen, still in the first line, I say that write a W there, as I showed it to you. So if I flip the switch, then there will be a W, and that tells me that I'm writing on the SD card. And otherwise, write a 0 there, as I showed you. So in that case, I know that there is no writing. So we are just displaying the data, but not putting it on the SD card. And then this is just the same exercise, very same. What is different here is I put the elapsed time in seconds in the third line. And then actually there is a fourth line, and that is empty now, but maybe in the future I will come up with something and use that line as well. So this is all about the printing on the OLED display, and then this is the serial. I just have this generic format. So first comes the time, and then I have a space or any kind of separating character. I like the space. And then I write two digits. Since our precision is 0.25, 2 digits is more or less acceptable to see. So then first value, second, third, fourth, and that's all. And here, when I write the last one, I make a line break. So when the same function comes again, this will be written in a new line. I will show it how it works. So then here, if our switch is switched on, then we open the file and we write in it. And then here comes the trick. We go to the end of the file and we start the writing from there. Therefore, we are not rewriting the file, we are just getting to the end of it and we continue writing there. So this is very important because this is basically the appending of the file, and I really want to use that because sometimes I just take a pause in the measurement and then I want to continue, and I don't want to remove the card, read the file and put it on my computer and then go back and do it again. But then I know that, okay, the last measurement was this, and it went for, I don't know, 2000 seconds. And I know that, okay, the second measurement was that, and it was running for 3000 seconds. And I can just manually then process the data in my software where I plot the charts. So then the same formatting again. This is basically the same that you can see on the serial terminal, and that's all. And here I just print a message to know that, and this is just a debug function. So I just want to know that, okay, and this part was successful. But I also let myself know if something was wrong. This is written if there is no SD card in it, and I will show you how it works. And here we don't do anything. So we just neglect this part. And then we arrive to the final part, which is the read switch state, but basically that is the first part, so that is here. So if I go back down, So we have to do a digital read, and this is also somewhat time consuming, so this can slow down the things. So maybe you don't want to do this in every loop, but it doesn't matter, because here we don't want to measure quick temperature changes. So we read the file on-off button, which is a switch, and if it's high, and if the switch status was false, then we flip it to true, and we reset the time. And I think this is a neat function, because whenever you stop the reading and you restart the reading, so for example you start a new reading into the same file, then you don't continue with the elapsed time, but you restart the timer again, and you start from 0, and then it will count from that 0, 1, 2, 3, 4, and so on. So for me this is very useful, because this is another guide that helps me to distinguish the different measurements, because then I see that, oh, there is a 0 time, so I most probably started a new measurement there. So then we reset the time, and then we enable the writing. So that will allow this function, the write SD, to enter this part and write on the SD card. And again, just some for debug or checking things that I print on the terminal, so I know that the switch is on. And if this doesn't happen, so if the other thing is valid, which means that the file on-off button is low, then of course the switch status is off, and we do not enable the writing, and we also print off on the terminal. So basically this is the working principles of this software, and I will upload it to Pastebin, so check it out and change it to your own taste. And now I just show you the terminal. So here I open the terminal, and you can see the message. So I just turn this off. So locating devices, found 4 devices, and I have 4, so that's pretty correct. And then here you can see the error message. There was no SD card, and we see that it is off here, which means that the toggle switch is off, so there is no logging on the SD card. And here you can see the time in milliseconds, and this is like pretty much 700 milliseconds and a little bit more. So here you can see 4, 7, 23, and so on. And you see the 4 different temperatures, and they are at the same spot, so I'm not expecting 2 different values from them, so this is quite nice. I turn on the auto scroll, and now I just flip the switch. Of course this will generate another error message, but it should change the off to on. So I flip the switch. First of all, here was still off, but here you see it on, and the timer was restarted. So it starts from 0, 720, and so on and so on. And of course we get the error message because we were not able to write the file. But still, it goes on. It will not stop us from the measurement itself, but it will not write anything on the SD card. So now I flip back the switch, and the timer will be not resetted. There will be a message off, but otherwise the timer will continue, because there is no need to reset it here. We can reset it only when we start the measurement again. So listen. So you see, I flipped the switch, and now the time is continuing there. So there's no change in the order of the magnitude of the numbers, and you see that it is off. And what I do now, I disconnect the device, and now I try to insert the SD card. So SD card is in. Please listen. Device is connected. So this goes white now, of course. I just reopen this thing. So now we are logging but no, we are measuring but not logging, so it's off. So now I go and turn the measurement on, and you get the success messages. That means that we are writing the data on our SD card. And now I turn it off, and now we are not writing on the SD card. So basically that's all. So you could see the drawing, you could see the device, how it looks like, what are the dimensions of it, how it works, and so on and so on. And finally we saw the code also in action, and also I tried to explain all the details that I did. So once again, I will upload this code. I think it doesn't contain any errors, and as you can see it is running, so there's no problem with it. And yeah, I just want to ask you to please subscribe, at least in exchange for the code that I wrote and introduced to you. And I hope that this video was useful for you, and it helped you, or it was entertaining, or whatever. But I think that this kind of sensor is quite neat, because you can really utilize a lot of temperature sensors. So if you need a lot of parallel sensors used in the very same environment, then this should not be a problem. And you can see that the code for it is very simple. So yes, I hope you learned something. I hope that this was useful for you, and please subscribe and leave some comment if you have some questions, and see you in the next video.